In this lesson, we're going to take a look at the geometry nodes interface. So Blender has something called workspaces, and up here you can see the different workspaces you have. You have the layout, modeling, sculpting, UV editing, texture painting, shading, animation, rendering, compositing, geometry nodes, scripting, and a little bit more if you click on this plus icon. For this course, we are going to mainly be working in the geometry nodes. So these workspaces are just basically Blender organizing the interface depending on what you're doing. Because we are in geometry nodes, we have the 3D viewer, we have the spreadsheet, the node editor, the properties panel, and the outliner. Let's add a cube using Shift A, Mesh, Cube, just to show you what is going on here. So whenever you have an object in geometry nodes, you will have this spreadsheet that shows you data associated with that object. And in the spreadsheet, you can see the different types of data we have. We have meshes, curves, point clouds, volumes, and instances. Because what we have selected is a mesh, you can see that we don't have any data in the other data types. The only data we have is in the mesh category. We have 8 vertices, 12 edges, 6 faces, and you can see everything is just basically a summary of the type of data you have for the object you have selected. And if we go into edit mode, you can see for a cube we have 8 vertices, 6 faces, and 12 edges. Now you also have this attributes section, and you can just expand it to see more data if you have more data. And what it shows you is a more detailed view of the data you're looking at. So right now we are in the vertex category, so we are looking at vertices, and you can see each vertex is represented by an index. So if this is vertex 1 or vertex 2, vertex 3, let's say that, it gives you the vertex ID or index, and then its position in 3D space. So if I say select this vertex and move it around, you can see that it's associated with this data here, and you can actually visualize this data in the 3D view as well by going to the top menu, scroll to the overlays, and when you expand the overlays, you should see the attribute text to preview any attribute text. Now we haven't set up any geometry nodes modifier, so let's do that so that we can actually preview the data in the 3D viewer. Since we are already in the geometry nodes interface, you have this new button that you can use to create a new geometry node setup. It will create one in this interface, and it will also add it in the modifiers panel. Basically, it's the same thing represented in different areas here in the node editor and in the modifiers panel. We want to preview these indices or even the position data within the viewport. To do that, there is a node called node preview. But before we do that, let's just talk about what we are seeing right now. Now you have this node editor. The way you navigate it is if you hold down your middle mouse wheel, you can move the interface. And if for some reason you have moved everything far away from the screen and you're not seeing anything, you can use A to select everything and use the period key to center everything that is selected. Let's try that again. I'm just going to move this to the side, and since I have this selected, I can just use the period key and I will center that. And if it was just this, I can click on that and it will center that node. In geometry nodes, you have to start with an input and then end with an output, and between that you can manipulate that data and change it however you want. So right now, this group input is basically just getting data from the selected object. So whatever you have here is going to be represented in the group input as geometry. So we are bringing this geometry, this cube, inside geometry nodes and then outputting it right here. So we haven't done anything to it. But let's say we want to change a few things about this data. We can do it within this area. Say we can move this up using a transform node, and to add a new node, you just use Shift A to access the add menu. And you can see they are categorized in different sections, but there are a lot of nodes. It's very hard to memorize everything. But the good thing is that you have this search function, so you can search whatever node you have. You don't have to memorize every node, but as you use them, it's going to get easier for you to remember what node do you need. What we need is to transform this, maybe move it up, scale it a bit. So let's do that inside geometry nodes. So Shift A, and let's search for the transform. So let's select that, and you just drag this to the line, and you can see When you move it, the color of the line will change, showing you that it's ready to connect the node. And then now when we connect that, we can translate this up, rotate it, scale it. And if you want to change the values of all the axes, you just have to select one and drag down to select all of them, and now you can adjust them at once. I can also do it here. Just move your cursor on the first value, click on it, and then drag down, and now you are able to just do that. So you can see we have done some transformation on this mesh, and the data here has changed. So basically that's how you connect different nodes. And if you want to remove this, you can just select it, hold down Ctrl X, and that will remove it from the connection. Now if I use Ctrl Z, I can undo. If you just use X, that deletes the node, but will also delete the connections. Let's say we have another transform node here. I'm going to use Shift D to duplicate this and connect it here. So if I use X and delete that, you can see that it will terminate the connection and delete the node as well. Sometimes you just want to use Ctrl X to just remove that specific. In this lesson, we're going to take a look at the different geometry data types that are in geometry nodes. So let's go to geometry nodes and add a new object. Let's use a plane. Right away in the outliner, you see the main data types, and that is mesh, curve, points, volumes, and instances. Geometry nodes itself is like a different system within Blender, and you have to bring data outside of it into it. When you create a new geometry node setup, you're basically bringing in data into the geometry node system, and whatever mesh you have active is going to be brought into the geometry node system through this geometry input, and it's going to be taken in as geometry. And it doesn't matter if what you have is a curve and you create a new geometry nodes, it's going to be brought in as geometry data. Like I said, there are several types of data that geometry nodes accept, but the way to bring in objects into geometry nodes is through the geometry input and bringing them as geometry. For example, let's say we have this plane, and let's say we have this torus, and we want to use it in this geometry node setup. You can just drag this object into your geometry node system, and will also be brought in as geometry. Again, this doesn't matter if what you're bringing in is a curve. As long as geometry nodes accepts it, it's going to be brought in as geometry. Sometimes what you have doesn't even have any geometry data, like empties, or like an empty like this. Empties, because they are not actual geometry, you can't even apply a geometry nodes system on them, but you can still bring them in, and they will still be brought in as geometry, though they will lack any vertices, faces, or edges, but they can still be brought in as geometry. This cube here, this mesh here, because it's the original geometry, it's brought in by this group input, but you can choose to work without it by just using geometry that you imported in, like we imported in the torus through this object info node. And so we can just use that data, and you can see it will replace the original data. And you can use, say, a set position, Shift A to access all the nodes. So I'll just search for a set position, put this in, and I can manipulate the position of this geometry. If it was the original geometry, then you can see now I'm manipulating that geometry. I have an empty. If I connect that here, you'll see we won't even see that because it doesn't have any actual geometry to work with. But one thing you can do is if you set it as an instance, then you can see it. It tells geometry nodes that this is not actual geometry. Treat it as an instance. If you look in the spreadsheet here, you'll see that geometry nodes is trying to look for vertices, edges of whatever geometry we have put in and move it using this set position, but it's not seeing anything. It goes through the curve, it doesn't see anything. It goes through the point cloud, it doesn't see anything. And only if we use this as an instance does it recognize that, okay, there is an instance, and let's treat this as an instance, and it will render that as an instance like we have here. Like I said, there are several data types, including vectors, floats, integers, booleans, color, strings, vector 2D, rotations, and others. They're all denoted by different colors to help you understand what type of data you are working with. For example, if you're trying to move vertices around, let's go back to the original geometry and maybe even delete this using X. whenever you're working with position values, you're normally working with vectors. Vectors in 3D are just a way to represent coordinates of an object using 3 values. So for example, if we want to get the vertex here, it has a value in X, it has a value in the Y, and it has a value in the Z. So a vector like here is just a way to represent that data. And if we use a set position like this, we are basically just offsetting the X value or the Y value or the Z value. We're just adding onto that. So say if I want to move these vertices up a bit, I can add a value to the Z, a value to the X, to the Y, or a value to the Z. You don't have to remember every data type. What you can remember is that vectors are usually used to record or set positions or scale of an object. So for example, the position of this vertex could be say 0 on the X, 1 on the Y, and then 2 maybe on the Z, and that is going to be stored in a position vector. I also have a float value. For example, the size of an object can just be a float value. Say the size of this entire plane is 1. Maybe if we scale it by 2, we can say that is 2, and that value can be stored in a float because it doesn't have to be represented by 3 values. We just know that scaling a value is just a way of increasing the size of a vector. So we don't have to store all the values for each axis. We just have to know that we're going to scale the vector here by a value of 2. So that's where things like floats can be useful. Like I said, you don't have to remember all of this. You will learn these data types later as we continue learning about geometry nodes. In this lesson, we're going to look at how data flows in geometry nodes. So let's add a cube here and set up a new geometry nodes. Data flows from left to right, as you can see from the 2 node setups we have. We have the input, and on the right we have the group outputs. So the data should flow from left to right, just like that. So whatever node you have here will be run first, and then if you add another one, that will be the second node data calculated, and then the third as well. So let's try that. So let's use a transform node, move this up 1 unit, just like that, and then move this on the left another unit. So if I shift D, again you can see because I still have this value, it moved this 1 unit up and then added another unit. So now this should be 2 units up. So this should be 2 units, and now we can even measure that. So we started off when the whole object was around here, and we moved it 1 unit, and again moved it another unit up with this. And if I disable this using M, it goes back to this level, and if I disable this with another M by muting it, you can see where we started. We go up and we go up. Now if we change this maybe to a rotation, I'm resetting this Z position to 0 so that we don't have any extra translation. If I rotate this on the Y axis, you can see what happened is that we move this up and then rotate it. But take a look at if we reverse the order. You see how things have now changed. We don't get the same results because instead we started by rotating and then moved up. But if we start by moving this up and then rotating, you can see the results you get are a bit different. And one of the main reasons why the order of these nodes matters is because most of the calculations are done relative to the origin of the object. So the origin is just the pivot point, which is this dot here. It tells geometry nodes where the center of the object should be calculated from, basically the pivot point. So if we transform again, if we rotate this on the Y direction, because the pivot point is still in the center of the geometry, the object rotates while using the pivot point as its center. But now if we first translate or move this up, let me first reset the rotation and mute this, move it up, you can see the pivot point has not moved. Whenever you're working in geometry nodes, that's one thing you have to note, is that Geometry nodes is like editing the mesh within edit mode and never touching the settings of the object outside edit mode. For example, here you can see when we go inside here, we can edit the positions of these vertices in edit mode, but we have not touched the location, rotation, and scale of the object itself. Let me actually show this again. I'm going to duplicate. I'm going to just add a new cube. Now go into edit mode and move it up. If I go into edit mode and move these vertices, the cube itself has moved, but the position has not. If I rotate this in edit mode, I am rotating the geometry, but outside edit mode, nothing changes. If I scale this, outside edit mode, nothing changes, but we can see that visually things have changed. It's only when you scale things outside that this data changes. If we rotate this data changes as long as I'm outside of edit mode. If I translate this, you can see that's what is happening. So basically, geometry nodes is doing all these operations within its own mode. Imagine another mode here called geometry nodes, and that's what we are working in here. So whatever we're doing here is not affecting any data outside geometry nodes or even edit mode. You can see we still have the original cube in its original position while in edit mode, and the objects that are like positions and rotations are also not going to be affected by geometry nodes. That's something to keep in mind. And again, because calculations in geometry nodes are based off the origin of the object, when we first move this up, we have offset its position from the pivot point. So when we try to rotate this after we have moved it, it's still using the pivot point as the center of rotation. And when we do this before the translation, you can see that it's rotating this before it's translating it. So when this is happening here, you can imagine that this is disabled and it's being rotated and then moved. So this operation is happening before the move happens. That's why that you see that we can rotate this up here and the rotation looks like it's being centered at the pivot point while the pivot point is still here, because this is coming before this translation. So it's not really looking at this yet. So this rotation is not considering whatever is happening after it. So for this node, it's like this node doesn't exist at all. And then later you update the data. So even when you have this enabled, this will operate like anything that comes after it doesn't exist. That's how geometry nodes runs. It calculates everything from left to right. In this lesson, let's talk about point clouds. So a point cloud is just basically a fancy way of calling a collection of points. So if you use Shift A, add a plane, and set up a new geometry nodes. Let me zoom in here. You can see we have meshes, curves, and we have point clouds. In that data, we have 0 points. There are several ways to create points, including just converting whatever mesh you have into a point cloud by using a node called mesh to points. So if you use Shift A and search for mesh to points, it's basically going to convert all the vertices you have into points. And you can see now in the mesh we have 0 data, but in the points we have 4 points. Now if I go into edit mode and subdivide this mesh, you can see now we have more points. So we have 9 points now, and we can subdivide this further to add more points, and you can see what we have. This is geometry node, so there is no reason to work in edit mode. So let's do the subdivision within geometry nodes as well. So I'm going to undo this, Ctrl Z, 1, 2, 3. Okay, so until we have our basic plane. So instead of subdividing in edit mode, I can use the subdivision node. So if I use Shift A and add a subdivide mesh, I can subdivide this like this. Now notice that I'm adding this here before we convert this to points. Because remember, the order of execution is from left to right. We input our geometry, which is our plane here, and then we subdivide it, then we convert it to points. Now, if I remove this and put it here, you can hold on Alt and drag the node to just remove it from the connection. And if I move it after the mesh conversion, you see we get an error here. Geometry nodes is trying to tell us that you're trying to subdivide points. So I'm just going to remove this I'm holding down Alt to remove it and letting go and dropping it on this line to bring it back. So I can subdivide this here, just like that. You will notice that if you drag, this value ends at 6, it won't go beyond there. And the reason for that is that Blender is trying to protect the project. So because when you do a lot of subdivision, Blender is likely going to crash depending on how powerful your PC. So it's just like limiting how many subdivisions you can make, because the more subdivisions, the more power you're going to need to calculate those subdivisions. And actually, as we are talking about that, we can even bring up another point. If we go to this top right corner, you will see the overlays menu. We have timing. And this is going to just show you how much each node costs to compute. The more subdivisions you have, the more it's going to cost to calculate that subdivision. So you can see if I bring this up, it becomes a bit more expensive. That's something to keep in mind as well. If you want more subdivisions, you can type in the number directly. Let's say 7, and you can see we're getting a lot more subdivisions now. But again, it's always recommended to not go beyond 6. Now, this way of creating points has a few issues. You can see that it depends on the number of vertices we have. So it's going to recreate. So if you have a plane subdivided like this, you're going to end up with a grid-like formation. That could be something that you might want, but in most cases, you're not going to want things to be laid out, points to be in a grid format like this. You might want something more random. And to show you this more easily, I'm going to add a monkey head here. If we create the same node setup, adding a subdivision and then a mesh to points node, we can have the same. Let me create a new one. So we had a subdivide mesh, and then we converted mesh. You can use mesh to points. You can see that it's just converting every vertex into a point, and we have that. Now, to be more efficient, if you want to use the same node setup on other objects, you don't have to recreate them from scratch like we have done here. Every node setup you create is going to be stored in a list of geometry nodes setups. So we have made a few copies. So let me just call this one point cloud. Instead of recreating this, I can just, let me first delete this by hitting the X. I can just search for it in the node list and reuse it here. So everything I do here is going to be recreated here because these are using the same node system. You can tell from the name that it's the same node, and the node setup itself will tell you the number of users using that node setup. So if I duplicated this, you can see now we have 3 users using this point cloud node group. So if I duplicate this, so any changes we make here are going to be the same for everything. So for example, if I change the radius to 0.001, you can see all of them get that. If I remove this subdivision mesh, Ctrl X to dissolve it, you can see I get the same thing. But because these monkey heads have more points originally than the plane, they get more points. There is another way to create points more randomly on a mesh, and that is by using the distribute points on faces node. So if I use Ctrl X to go back to the original mesh, I can search for distribute points on faces. And if I plug this into the node group, you can see that we are basically creating points randomly on our meshes. This gives you more randomization, and it's not based on the number of vertices you have. And another thing, you will see that this costs way less in computation than subdividing a mesh. If I bring back the subdivide mesh, so subdivide mesh and just replace this here, and we have to mute this and use mesh to points. That's here. Bring it here. You can see that if I subdivide this, this is costing me way more, and you can see how many points we are achieving here. So we have about 1.1k points, and it's costing us 54 milliseconds. Now if I disable this and unmute this, you can see we are creating 1.7k for 0.11 milliseconds, yet here we were about half a microsecond. So this gives you more points at a lesser cost and more randomization. That's point clouds. In this lesson, we'll continue with point clouds and looking at how useful they can be. So I'm just going to remove these nodes here using Ctrl X. And now what is the point of all these point clouds? Well, points are great because they have data. Like if you go to the spreadsheet, you can see the type of data they hold. They have position, they have ID, they have radius, they have UV map, and they also have index. This is just a unique value for each point you have. And they don't cost a lot. As you already see, we can have hundreds, even millions, without it costing quite a lot, as you can see here. Since these point clouds can hold a lot of data, we can do a bunch of things on them and then replace them after those calculations with other objects. Let's make a quick tree here. I'm just going to add a circle and let's use about 6 polygons. Imagine this is our tree. We're going to create a simple low poly tree. I'm going to go into edit mode, fill it using F, and then insert using I, and drag this up. Just a low poly tree. I'm going to add a few subdivisions just like that. Now maybe let's create a simple tree. I'm using Ctrl R to add an edge loop and then scaling it in just like this. And let me select this edge loop, hit F, insert it, and this is our tree. Select everything and bring this up so that the pivot point is at the bottom. That way, if we are trying to rotate, we can do that. If we are trying to scale, we can scale it from the pivot point there. Now, I'm also going to go under shading and turn on randomization so that each object has a distinct color. Now, you can do a bunch of things on them and then replace them with other things like a tree. So let's start small, like with 10 points, just like that, and bring in our tree. Remember, we can just drag it in. Actually, let me first rename this to a tree, just like that, and drag it into our geometry nodes as new geometry. So we can convert each point here into any object we want. The way we do that, you use a node called instance on points. Basically, each point is going to be converted to whatever geometry we input here. So I can just drag this in here and you can see what we have. Now, if you look at this instance on points node, you see that it has a bunch of information that it uses, like rotation. If I rotate this on the X, you can see every instance is getting rotated. We can rotate this on the X, on the Y, and on the Z. And we also have a scale value. I remember when we are talking about data types, this scale is a vector value. If we want to scale the tree, we can scale it in the Z, and then in the Y, and then in the X. But if you want a uniform scale, these values have to be the same. So you can drag from the top down and that will select all the inputs. And if you hold down Shift, you can slowly increment the values. One thing about Blender is that it can let you connect different data types to different data types. For example, if I bring in a float value, you can just search for value and that will give you a float value. I can just use this value under the hood. It will be fed into the different inputs. So if I bring this up, I'm going to hold down Shift to slowly increment this. These values should also be the same. And if you move your cursor over this, you can see that we have 0.2229 for every axis, which makes changing this more easier than having to do this for every axis. You can also duplicate this and plug it into the rotation, but that means that all the axes you have are also going to get the same value. And for the rotation, it doesn't work very well. Another thing you will notice is that the object info that we use to input our tree also has some outputs like transform, location, rotation, and scale. Now, if we plug in the scale of the object into the scale of this, that means that we are using the original object scale as the scale of the tree. So we can just scale the original tree here, and the instances will be scaled as well. Same for the rotation. If we plug this directly into the rotation and rotate this, you see that we get the same thing. But you normally don't want this. You normally want the trees to be randomly rotated, randomly scaled, and randomly positioned. Instead of doing that, you can look at the distribute points on faces. Like I said, points can hold a lot of data, and distribute points on faces node also adds information to our points, like the normal and rotation. Now, if we plug the rotation into the rotation input of our instances, you will notice something. Actually, let me first remove all of these. Remember, these were the original monkey heads that are using the same point cloud system. So this rotation you're seeing here that is given to these points is not really random. It's based on the direction of the faces. So if I disable this node for a second, so each face is getting a point, and so for example this face here has a normal direction pointing that way. So this is going to be translated into a rotation for that point and stored onto that point, so that it can be used later, and for example instancing on points. And that's what is happening here. Let me scale down these trees just a bit, the original tree just a bit, so that you can easily see what we're doing. Let me scale it down even further. And one other thing we could do, you can bring back the original geometry, or you can join multiple geometries together by using the join geometry. So join. So if I plug it in here, you can see it's even bigger, letting you know that it can accommodate more than one input. If you see a dot like this, that means that it only takes in one input, but this can take it multiple inputs. So if I drag a connection from the original mesh, which we can preview by just dragging this directly into the geometry, bypassing everything else. Let me do this here. You can see how the original geometries look like. Again, we're using the same instance of geometry nodes on two different objects. But if we join this here, and let's preview this, you can see that each instance is taking on the orientation or the rotation of the face is set on. Okay. In this lesson, we're going to take a look at creating custom inputs. So we have this geometry node setup that we are using to create forests on different meshes. Let's rename this to forest generator. Let's say we want to have different versions. Maybe we want another one that is more dense, another one with larger trees, and another one maybe with, I don't know, we will think of something. So we can all make sure that they're all using the same generator. If you try accessing the forest generator directly from the list, you'll see that it's not being added. The reason for that is because geometry nodes is actually a modifier. And when you try to add a geometry node setup without the modifier first, it fails. So you need to make sure that you have geometry nodes modifier first and then add in your forest generator. You can now either do it here or do it directly here. We want this to be taller, but the problem is if we scale this here, it's going to be scaled for every instance. So what we can do is, instead of using the scale of the original object, we can just disable this, and let's reset this to be uniform and maybe scale them down. I'm holding down shift and then dragging from the top down. Okay, so what we can do is create custom inputs or custom parameters. These are just going to be exposed inputs here, so that each instance of our geometry nodes can use unique values. So let's start with the scale value. The group input brings in data into geometry nodes, and we have already looked at the geometry input. Basically, whatever object you have, let's say a cube, just like this, is geometry. And when you create a new geometry node setup, this geometry is going to be brought into geometry nodes through the group input through this output here. That's why you see that though we are using the same instances of the forest generator for all these meshes, and actually I can even do it here, they don't look the same because the underlying geometry or original geometry is different. Now, if we skip this and say use a grid, which is basically a subdivided plane, and if we bypass the original geometry, you can hold on Control to disconnect whatever input, whatever connections you have, and plug them to a different mesh. Now you see what we have. Every object now has turned into the grid with the forest system. That's because this is our first custom input. We just don't have it exposed here. So I'm just going to just use Control and then drag back to this so that we're using the original underlying geometry for our forest system, just like that. Now let's create a custom scale by just dragging the scale into this new slot. It will create another slot in case we want to input anything else. But yeah, we have this. So now each instance has its own scale input. Now, if I scale this up, we get that. I'm scaling all these so that they are uniform. You can see I'm only scaling what I have selected. So I can make these maybe taller, then maybe make these wider on the X. So you can see we can make everything unique for each data. Now, when you're working with scale, you normally want uniform scale. You rarely want it to be scaled in one axis more than the other. So exposing this as a vector, just like this, kind of makes it harder to do uniform scales. So what I normally do is, if you press N, you will see more settings and more panels. The first panel is going to be the group panel, basically the general settings for the geometry node setup you have. That includes group inputs and group outputs. Now, if you look at the group sockets, you see that we have our geometry, this here, and our scale. We also have outputs that are on the right and inputs on the left. If you can see that we have that here, and you can rename these. So let's say out, and you can see that it will be renamed here. The outputs are always on the right and the inputs are always on the left. So I can rename this to mesh or data in. You can see it's renamed there. And for scale, we can keep it as a scale, but what we want to change is the data type. We don't want to scale all the inputs separately. We want to use one value to scale all the inputs. So I can change this from vector, which uses 3 types, to a float. So I'm just going to go to the type and I look for float. Now, sometimes, depending on the version of Blender you're using, this connection might be disconnected if you change the type. If it is, just reconnect it, just like that. And now we can make sure the default is 1 so that we always have something. If we look at the inputs in our modifier, you can see that now we have a scale value. So I can do this. Now I can also come here and make sure that this is 1, just like that. Now we also can expose things like density. So I can drag this to this. You can rename it whatever you want. I'm just going to keep things simple. Let's say 100. So that is a really dense forest. And remember, because we're using the underlying geometry, we can go into edit mode and edit this. And that will also change the underlying geometry we are using in geometry nodes, giving us something that is more interesting, just like that. In this lesson, we're going to look at data preview. Let's say we have a plane. I'm going to scale it up and then create a new geometry nodes. So I want to subdivide this a few times using a subdivide mesh. So Shift A, subdivide, just subdivide it a bunch of times. Let's go in the overlays and turn on wireframe so that we can see the different subdivisions quite easily, just like that. Geometry nodes has 2 outputs. There is this group output and also the temporary preview. So if I hold on Control Shift and click on any node, I can temporarily view everything that has been calculated up to the node I'm previewing. Say I have subdivision here, but if I want to bypass this subdivision, I can hold on Control Shift and then click on this. That way I can preview everything up to this point. Let's say we transform this, move it up a bit. I can preview just up to this part, and you can see we have transformed this. If I just hold on Control Shift and click this, you can see this we are previewing before that. If I do another transform here, but this time instead of translation, I rotate. I can preview up to this. So you can preview what is happening at any point in the geometry stage by just using the preview node. This is also used for previewing different data. For example, if you wanted to preview the position of each of these points, there is a node called position. Basically, that reads all the positions of individual vertices, points, edges, curves, anything you have. So if I use Ctrl Shift click, I can preview those positions. Geometry nodes gives you a color visualization of different data types. So for vectors, it will just give you this color gradient, giving you blue for the Z, red for the X, and green for the Y. And actually, we can preview that. We can bypass all these other nodes and go right to the subdivision. Look at that. But we're still previewing the position node, and you can see that the more the points go in the X direction, they become more red. The more they go into the Y direction, they become more green. The more they go into this direction, they get a mix. And if they go in the Z, let's preview here, they should become more bluish. And actually, if we change these values here, you can see that we get that, just like that. If you move this on the Y, and I maybe remove the most of the Z, you can see these points become more greenish. You can also preview the actual values of these individual points by going into the overlays of your 3D viewer and turning on attribute text. This will just preview whatever value input data type you have input here. Because this is a vector, these should be 3 values for each point. Right now we have too many points, so I'm just going to reduce those so that we have a few, and you can see that each point has a vector position of 3 values. So that's one way to preview data, but that was just position. There is also other values like rotation. Now we don't have a node that reads the rotation of each vertex because vertices don't really have rotations. Even faces don't have rotations and edges don't have rotations. That's why we don't really have any of that. If we had instances like we had before in our forest project, we could easily visualize that. And let's try doing that. I'm just going to use a distribute points on faces, and we should have our points now. Yeah, here. It's as many. And if we preview our the normal, you can see they all have a normal facing up because our original mesh, if we preview just that, our original face also had a normal pointing up. And actually, if I just, there is a node that reads the normal of each face or point. So we can access that by just using Shift A. And you can see that each vertex has a normal facing up. And I can tell by just looking at this vector. So that is going to be transferred to all the points that are added to that face. Now, if we had multiple faces, let's go back to the original mesh and subdivide this. And I'm actually going to first remove this normal preview because it's getting in the way. Edit mode and subdivide this a bunch and select some of these points and just bring them up just like this. Let's preview the normal now. Let's use fewer points. And let's join back the original geometry. So join geometry so that we see how these individual faces are facing. Now we are looking at the normal of each vertex, but we can also change the preview from vertex to point by just changing the domain here. You go to the viewer. Let's look at the faces. So we're trying to preview the normal of the individual points from this node. But remember, these are now converted to points, so they don't have any faces. that we are previewing. If we go back to points, you can see that now these points have actual data, but because we are previewing also the original geometry through here, we're getting a lot of points and a lot of clutter. So I'm just going to bypass this for a second, and you can see that each point here has normal information that we are previewing. If we just preview the original mesh, we can switch to faces, but you will notice we are still seeing 0, 0, yet for this we should have a normal facing that direction and a normal facing this direction and others facing whatever direction like that. And the reason for that is because we are pulling the normal, we are reading the normal of the distributed points instead of this geometry. So to read the actual normal of this geometry, we need a separate normal node, and if we plug that in, you can see now our mesh have now normal data for our faces. There are a lot of different data types that have visualization, so we'll take a look at that when we come to those data. In this lesson, we're going to look at attributes. So attributes is just data stored on geometry. For example, we have a plane. Let's subdivide it using a subdivide mesh. And let's look at the wireframe. We have already worked with attributes like position, scale, rotation. Those are all attributes, and they can be stored onto every point, onto every edge, onto every face, as you can see here. And the first attribute always is the index, which is basically an identifier of whatever data you're looking at. We can actually preview this using the index node, which reads the index of each individual data you're looking at. So if we preview this using Ctrl Shift and then clicking on the index, let's preview the geometry after it's subdivided. If we go to the overlays, we can bring back our attribute text. And then let's take a look at the faces. Let's reduce the subdivisions. So we have 0, 1, 2, 3. They're all over the place, depending on how the mesh is subdivided or how data is created. So these are faces. So each face gets a unique value. If we go to points, each point has a unique value. The first one is always 0, and then 1, 2, and above. You have faces, you have edges, and if you have face corners, you have splines. Because this is not a spline, this is a mesh, we don't see any data there, and you can actually see that in the curve editor under spline we have no data, so we won't be able to preview anything. And instances, we don't have any instance, but there is a node that you can use to convert geometry to instances, geometry to instance. If I plug that in, now this becomes an instance. So we have one instance and 0 meshes, and this entire thing becomes 0, giving it an identifier of 0, since indices all start from 0 and then count up. So what can we do with these? Let's first remove this and make sure it's looking at auto so that we see everything we want automatically. So let's subdivide this again. Like we have seen, each point, each face has attributes like positions, and we can change those attributes. We can manipulate those attributes. For example, the position can be manipulated in many ways, and one of those ways is using the set position node. If we offset the Z value, we are changing the position attribute in the Z value. We can do this for all the points at once, or we can do it individually. So for example, if I move this up, you can see we have moved all the points, but we also have a selection option here. You can select based on a lot of things, including the index. For example, if we go back to our index reader, so if I bring back the index, preview that, and let's preview faces. Let's use fewer subdivisions. Let's say we want only to move the face at index 0. We can select it by using a compare node. Just search Shift A, search compare, plug it in here, and you can even preview the results of what you're doing. We're trying to create a selection of only the index 0, so we can use equal to 0. And it visualizes this by giving the value you have selected 1 and everything else 0. So 1 is for selected and 0 is for non-selected. And you can even see the color visualization. 1 or white is for selected and black or 0 is for non-selected. So this epsilon is just threshold. So if you're trying to expand your selection, you can increase this epsilon, and so now we have increased our scope of our range from just 0 to maybe include values going above 1 up to maybe 4. So it's like using the greater than. So if we are selecting just values greater than 0, you can see those are all selected. If we increase this, you can see that index values of anything greater than 0 have been selected. And one thing to note is, depending on the data type you're previewing, the will change, because we are looking at this greater than node. I've muted it right now, but if I bring it back, you can see that we have changed to a true and false statement, because this greater than is a Boolean operation that gives you a true or false value. So that's why we are looking at that. So circling back to the set position, if you wanted to just move the face at index 0, we can just change this to equal to 0 and bring back the offset, or remove the epsilon and set it to 0. And we can now use this as our selection. But you can see we're moving this vertex instead of the face, because this set position doesn't have the option to select between faces and vertices. And if we preview the index here, yeah, this should be vertex 0. So if we take a look at that, yeah, this is supposed to be vertex 0. That's why it's moving up. And if we increase the range, you can see we are starting to grow our selection. In this lesson, let's take a look at Vertx manipulation using geometry nodes. So we have our plane. Let's add a new geometry nodes and subdivide it. Shift A, subdivide. Subdivide this quite a lot. I'll bring back the wireframe. Since vertices hold data like position, as you can see here, we can manipulate that using the set position. A, set position. Again, you can do this for everything, or you either use a selection or you can use a texture. So geometry nodes has a bunch of textures like the shader editor. So if you use Shift A and go to the textures, you can see we have a brick texture, checker, gradient, image, magic, and others. Most of the time you're going to be relying on the noise texture, so let's use that. We have already looked at previewing data, so let's preview this noise. So if you hold down Ctrl Shift and then click on the node, I can preview that node, but it requires some geometry, so you can decide where in your node tree you want to preview this. So I'm just going to hold on Ctrl Shift click and preview this here. So that's before the subdivisions, and here is the subdivision. You can actually see the noise. Now if we add more subdivisions, you start to see more information. Let me turn off the wireframes for a second. You can see that we are seeing more data. When you have less points, you have less points to capture this information. Just imagine them as pixels. More pixels mean more detail or more clear image. But that also increases your computation time, and you can always look at that in the node editor overlays by turning on timing. This noise can be used to change the position of each vertex. So if I just plug this directly into the offset, and let me just connect the preview so that we're looking at this, you can see that it's changing the position of each vertex depending on whether that vertex is lying in a black zone or in a white area of the noise. Now, the reason why this is moving diagonally like this is because, remember, we have different data types. We have vectors and we have floats. If you plug a float into a vector is basically a value, an input with 3 values. So if you plug a float, it's going to share that value everywhere. So when it shares, say, 0.5, 0.5, and 0.5, it ends up shifting that in that direction. Actually, let me see if I can visualize it here. So yeah, you can see that it ends up pushing everything in that direction. But because some of these are in white areas and some are in dark areas, some are going to be pushed more, some are going to be pushed less. That's why we get that overall direction. Another thing you will notice is that this has also shifted the entire thing from the center. And that's because the noise comes with an offset value that you normally have to subtract before you use it. So you can use a math node. This noise is a bunch of values placed in different areas. So you can subtract values to that. So here we're just going to subtract. I'm going to change this operation to subtract. I use Shift A and then search for math to get this node here if you're trying to look for it. So the noise texture comes with an offset of 0.5. So when you subtract that, this places back the noise in its original position. So we don't want this to go diagonally like that. We want to influence the noise in one direction, say in the Z or in the Y. So I'm just going to, instead of plugging this into the vector, you can actually split this into 3 values so that you have access to individual axes. And the way you do that is using a node called combine XYZ. So just use Shift A and search for combine, or just type in XYZ. That normally brings the 2 nodes associated with combining and separating the nodes. So I'll just use the combine, or you can import whatever value you want and then plug it into any vector. So if I plug this here and plug this in the Z, you can see that this is just going in the Z direction. Now, if I want it in the Y, it can go that way. If I want it in Z, in the X, just like that. But normally, you always want it to be in that direction. Now, another way we thought of doing this was using the selection. So let's first move this up, and still you can use this in the selection, just like that. And the problem with that is that when you're using selections create Boolean values, so a true or false value. So you won't have any gradients like what you have here. You won't have any areas where the value is between black and white. So if I preview just the noise, you can see in some areas the noise is not fully white or fully black. Each data type has its own color. So floats are going to have a gray color, geometry is going to have a green color, vectors are going to have purple color, booleans are going to have a pink color, just like that. So when you connect any output into another input, it is going to be automatically converted to that output. Since we are connecting a float output into a Boolean input, the float is going to be converted into a Boolean value, or true and false values, which are going to get rid of any slopes that we might have in the geometry. So let's remove the preview, and this is what we have. Now, there are so many nodes in geometry nodes. Some of them you will have to learn as we go along. You can add something like a subdivision surface. And there is also another one I usually like to add, that is the shade smooth or set shade smooth to make things look more smoother. And the noise texture itself comes with values that you might be familiar with, like the shader editor. So if I scale this up or scale it down, you can see I can create some nice displacement. Okay, so we're coming to the close of this section. So let's combine the knowledge we have learned and try to create a forest generator. So let's add a plane and let's create a new geometry node system. Let's first distribute points on faces, and we're also going to expose this as a parameter so that we can increase the density as much as we want. The other thing we want to do is instance on points, but first let's create our tree. Let's create a low poly tree here. Okay, so we have our tree. Now let's bring it in. Let me first rename it, and then this will be tree. Now let's bring in our tree and instance on points. with the instance on points geometry nodes, and connect this as the instance. This should be tree. I can even hide the original tree here. And for the scale, let's expose this vector. But again, we don't want to control these individually. So I'm just going to press N on the keyboard and go to the group sockets and change this from the type from vector to float. Again, if it disconnects when you change the type, just reconnect it. Now I can bring this up. Now, if you want this to be a bit random, we looked at a noise texture. And if we just bypass everything here and take a look at preview just the points, and let's increase the density to something like 1000 so that we have a dense number of points, bring in the noise texture. So if we preview just the noise, Control Shift and then click on this, you can see that even this can be used on points. And if we take a look at the instance, you can see that the noise is also working there as well. If we change the domain to instance, you can see that this noise is working there. And so we can increase the scale of the noise just a bit like that. If it's needed, you might want to even subtract the offset that comes with noise. And yeah, that gives us something like that. Now, instead of using the scale value from our custom parameter, we can just use the values from the noise and plug this in. Let's take a look at this. Now, noise values can range from negatives to positives, especially if you have a subtract value to remove the offset. If we don't have that, you can say we'll only have positive value, but usually that doesn't give you the right noise values you need. So I'm just going to unmute this so that we have the subtract and turn on clamp. That way we can cut off any values that go in the negative values and also cut off any values that go beyond 1. And we can even preview this by just duplicate this and multiply the noise. Let me turn off the clamping. So you can see that I can scale this up, but when everything is scaled to a value of 1, the scale just stops. And when I go to 0, we don't have any data anymore because we have this clamp on. If I turn that off, I can scale to as far as I want and below as I want. So let's just remove that and turn back clamping. That's what we have. Let's bring back the density to something reasonable, like 10 or more. So you can see what we have. We can also do more, like use a transform node before the distribution. So if I do a transform node here, I can actually bypass everything by holding down Control Shift, clicking this, and just previewing this before the transform. And let's turn on wireframe for a second. And I'll subdivide the mesh, Shift A, subdivide, get more subdivisions, and just displace this a bit. And the reason why I wanted to add a transform is because I want to be able to scale this forest, and we already have a custom scale input, so I'll just use that here so that I can scale this like that. And now I can use a set position because I want to displace this the way we were doing it before. So I can use a set position, and you can see I'm doing this outside this setup just to make things more readable. I can duplicate this noise and again separate, use the combine XY to create a vector so that we have individual access to all these axes, and just plug in the noise. And again, you will have to subtract. I'm just going to duplicate this, Shift D, subtract the offset that we normally have. And you can see because we have clamping, we're basically removing any negative values, and I think that's okay. I'm going to scale this down so we have something like this. And instead of just using this as the points, I'm just going to use the displaced noise, and you can see that displacement now comes through our mesh. Now, if you want to increase the strength of the displacement, you can just multiply the noise. Don't do it before the subtract, do it after, because the subtract clamps the value. So make sure you unclamp this and multiply. So now you can scale up this. So now if we preview everything, we turn off the wireframe, you can see our forest. I can add a join geometry here and connect the original geometry just like that. Actually, not the original geometry, but the geometry after it is displaced. So we can look for it by just using Ctrl+Shift+Click and clicking the noise until we find the one. Yeah, I think this would be it. So let me disconnect this, connect this, and we have that. Our forest generator. You can even go to the loop dev and take a look at that. You can go to the render settings, turn on ray tracing, so you can see your forest. Again, we have some exposed parameters like density and the size of the forest, but you can expose quite a lot. Like I think this is the scale of the individual trees, so I can expose that and you can name it whatever you want. So just go under, we can call it tree scale.